This is Kevin Cole at the University of Nebraska. The topic is thermodynamics, and the example is pump, velocity and power. We're looking at a water pump, and we've got 80 kilograms per second flowing in a certain diameter pipe, and we're told it's to be pressurized by 2 megapascals, or about 20 atmospheres. We're looking for the velocity at the inlet and outlet, and the power required. And again, we're told the pipe inlet diameter, 20 centimeters, and the outlet diameter, 12 centimeters. It's steady flow, so it's going to be inlet mass equals outlet mass. Standard assumptions for a pump are steady flow, no heat transfer, and if this is water, then we're going to take it to be an incompressible fluid. If there's no heat transfer and the fluid is incompressible, there's no mechanism to change the temperature of the fluid, so we can take the temperature change to be 0. Now, we're told nothing about the elevation change. Elevation change for water can be important. Because we're told nothing about it, I'm going to say that the elevation change is 0. We'll get to the energy balance in a minute. For part A, to find the velocities, we're going to use the definition of mass flow rate, which is area times velocity divided by specific volume, or we could solve for velocity, but we need this specific volume. We're going to get it from the saturated water table. We're not given a temperature, though. I'm going to assume a temperature. I'm just going to grab one. Let's say that T1 and T2 are 10C. So that's going to be our input information into the table. Saturated water table, let's go find one. Here's a saturated water table for temperature, and we're looking for the conditions at 10C, which is right there. Here's the column for specific volume. We're going to approximate the compressed liquid properties as saturated liquid. Now, the reason I wanted to show this table is that this is a nasty one. This says that the given value in the table has been multiplied by 1,000. So the value of 1 here needs to be divided by 1,000 to get us the proper saturated liquid specific volume. So 1 divided by 1,000, going back to the document, the result's going to be from the table, from the saturated water table, the temperature table. And which book was that? So that somebody else can follow your work. We found that at T equals 10C, we found that V was 0.001 meters cubed per kilogram. All right, before we find velocity, we need to find a couple of areas. Let me scroll up a little bit here. Area 1, the inlet, is going to be pi times 20 centimeters, or 0.2 meters, squared divided by 4. When I compute that, I got 0.03141 meters squared. And while I'm at it, let's take area 2 is going to be pi times 12 centimeters, or 0.12 meters. Square that, divide by 4. Then this number is 0.01131 meters squared. Hope you can check that. So let's use the relationship here for velocity. So V1 is going to be my mass flow rate. I'm giving it to be 80 kilograms per second. Multiplied by the specific volume we looked up, 0.001 meters cubed per kilogram, divided by area 1, which I just computed, 0.03141 meters squared, and that, when I compute that, I get 2.547. That fit on the page? That's in meters per second. Rather than compute the other one in detail, I'll just say similarly. I hope you can show that V2 is the same except for the area is different, and for V2 I get 7.073 meters per second. So those are my two velocities. That takes care of part A. For part B, we're going to think about the energy balance. This is for an open system with one inlet and one outlet. Standard assumptions are it's steady, so the time derivative term is gone. So let's get rid of that, steady. We're told there's no heat transfer, so the Q dot term is gone. And we're told no information about the elevation change, so let's say we don't know what it is, or the pump is small. And that is the form I'm going to use here. Let's pull this down. I'm going to get that W dot move to the other side of the equation, is going to be m dot times H1 minus H2, a change in enthalpy of the fluid, plus the kinetic energy change, V1 squared minus V2 squared over 2. Now, we need the enthalpy, which for compressed liquids is a function of temperature primarily. But I really don't want to use the compressed liquid table, so I'm going to use a trick. I'm going to say, recall that H equals U plus PV. And then I'm going to write H1 minus H2. H1 minus H2 can be written as U at T1 plus P1 times little v minus U at T2 minus P2 times little v. Now I wrote little v without subscript because it's incompressible. It's the same value both times. Now, the temperatures are the same. T1 equals T2, so that the internal energies cancel, and what I have left is a pressure change. I've got P1 minus P2 times the specific volume. I want to do one more thing. I want to write this as minus P2 minus P1 times specific volume. The reason I wrote it this way is that the purpose of a pump is to pressurize a fluid, and the final pressure minus the initial pressure, that's going to be the positive delta T, positive delta P that we're talking about, the pressurization. So that's what I want to substitute into the energy relationship. Okay, now that we've got that sorted, we know the velocities from part A, so we can find the, let's take this guy down here, and say that the work rate is going to be, let's put some numbers in, it's going to be 80 kilograms per second for the mass flow rate. Now my enthalpy I'm going to get from minus delta P times V. So I've got minus, my delta P we're told is 2 million pascals, newtons per meters squared, multiplied by the specific volume, 0.001 meters cubed per kilogram. Then I've got my kinetic energy terms. I've got V1 is 2.547 squared minus V2, which is 7.073 squared over 2, and the units there are meters squared per second squared. Now, earlier we did an example where we took this meters squared per second squared and multiplied by newtons over newtons, and then this converted to a joule per kilogram. And then over here we've got meters squared goes out, and we get Newton meters per kilogram, Newton meter per kilogram, but that's the same as a joule per kilogram, so the units are okay. So my units are okay here. Let me crunch the numbers. Let me crunch it in a couple of pieces first. Let me write it as W dot equals, I'm going to hold on to the 80 kilograms per second. And I'm going to show you the relative sizes. The pressure change times the specific volume gives me minus 2,000 joules per kilogram. My kinetic energy change is negative because the V2 is bigger. This one's minus 21.77 joules per kilogram. So this first piece comes from the delta P, and this piece comes from the velocity increasing through the pump. So it takes some work to pressurize and some work to accelerate. The pressurization is the big piece. It's 100 times bigger. All right, when I finish this, I'm going to get that the work rate is minus 161,700 watts, because the kilograms go out, I get joules per second, that's a watt, and that's the same as minus 161.7 kilowatts, which is about the same as a kilowatt. I can do better than that, kilowatt, which is about the same as 217 horsepower. Now this is a typical size for a fire truck, a pumper type fire truck. One of these trucks has a great big water pump in it, and they hook it up to a hydrant, and the power of the truck engine, a couple hundred horsepower, runs this thing. The other comment I would make is that W dot is less than 0, and that's appropriate for a pump because we've got work into the system, according to our thermodynamic sign convention. All right, so that's the work. Let's recap. We've got a water pump. We're told what the mass flow is and what the amount of pressurization we're getting. These usual assumptions for a water pump are that the flow is steady, there's no heat transfer, and if it's water, it's incompressible, so there's no mechanism for temperature change. We needed some properties. Well, we found the velocities from the definition of mass flow and from the size of the pipes. We needed some properties. We used the saturated water table under the saturated liquid conditions. When we needed an H value, we wanted to avoid the compressed liquid table, so we used the enthalpy and the fact that the temperatures were the same to find the enthalpy as a pressure increase times the specific volume. But we have to be careful of the sign there. And then if you remember that for a pump, the work should be negative because it's work into the system, then all will be well.